Thanks everyone for coming. Let me warn you, this is going to be the second least technical talk I have ever given. The most least technical being 2 months ago when I gave a talk on the same subject to a group of humanities faculty. So that's kind of the baseline. And somewhat to my amazement and maybe shock even, there's a lot of overlap in some of the background material here with Manuel's talk. The topic of my talk is causal inference, and somehow this talk is supposed to be, in terms of what I view it as, some kind of an invitation for people to maybe get interested in working in this area, which theorists really haven't worked in before, and in which there are, a bunch of genuinely technical questions that people can work on, but I'll get there rather gradually and not very much at all in this talk, but I'll try and give a taste. So first of all, what does it mean to even talk about causality? So this is a problematic concept, and it's been a problematic concept certainly for several thousand years, and probably a lot before that, except we don't have written records. And this really has to do with this concept of free will that Manuel talked about quite a lot in his talk. When philosophers, religious figures have generally talked about free will, it often gets bound up with the notions of the cause being responsible for something happening. And this carries over not just in language, but also in terms of moral and ethical and legal consequences as well. So you walk along and somehow an ox comes out onto the road and gores you. And the question is, who's responsible for this? Is it the ox? Well, certainly the ox chose to do it. Well, we can debate, and Manuel might have some interesting things to say about, where does the ox fall on this hierarchy? But certainly there are legal codes in which the ox is held responsible for this act. Maybe the owner of the ox is held responsible. Certainly if you look at laws nowadays in the United States about dogs that can be violent, the owners are often held responsible. Certainly if they have some knowledge that the dog is liable to go around biting people. Maybe the manufacturer of the fence is responsible. So we look at that and immediately we come into, well, there's a second category of apportioning guilt that comes up in certainly American legal codes. And there's this notion of proximate causes versus ultimate causes. There was a wonderful quote that Manuel gave in his talk, which is Dehane or something, or that the ultimate cause for something was maybe someone's genes, but that they had free will when they're actually going through some lengthy deliberation about what to do. And I think it's highly debatable whether the fact that you went through some long thinking about what to do suddenly gives you free will, And certainly here we come into maybe a more scientific way of thinking about this kind of question, which is that we basically think that physical law is deterministic. There are some complications here having to do with quantum mechanics. There are other complications having to do with thermodynamics, but we don't think that our brains somehow exist outside of physics. And physical law is, as far as we know, reversible at its bottom. So effectively, we can think of this as a deterministic process. At least that's how I would view it. And to me, that's a major threat to free will. And the fact that it took you a few minutes to decide in your chess move, to me, doesn't change that discussion the least bit. But anyway, this is sort of a long thing. My final quote on this subject is that this deterministic objection, this determinism objection, this objection to free will from reasons of determinism, doesn't begin with the scientific process at all. You can quote it from any of the world's major philosophies. I think, I didn't do an extensive survey, but I did, in honor of Vijay, take the trouble to find one from the Bhagavad Gita, which is this Krishna says, I know everything that has happened in the past, all that is happening in the present, and all things that are yet to come. So there's this notion that really the future and past are sort of laid out, just as much as space is laid out. And you should ask how free will can exist. Okay, but this is not a talk on free will, it's a talk on causality, but somehow we have to talk about free will when we talk about causality because it's essential to the notion of causality that someone is making a choice. You are choosing what to do in order for something to be the cause of something else. Otherwise, it's just the planets rotating and, just mechanically proceeding. There's no causes, there's just time law. It's just physical time evolution. So, and in fact, what I'm actually going to be telling you about in this talk is sort of much more down to earth, okay? It does have a basis in philosophy. The main basis goes back to the notion of counterfactuals in Hume's philosophy. But as a technical branch of work, it really arose in maybe the late 80s and the 90s by a whole group of people from statistics and AI mainly, and who the main figure I'll be quoting the most from is Judah Pearl over here at UCLA. And in this model of the scientific process, we sort of set our questions about determinism and reversibility to one side, and we say, here's a model of the scientific process. In the scientific process, there are experimenters or observational scientists. They can choose what to measure. They can choose what interventions to make. Your doctor can decide what to administer as a treatment. You can decide what to eat, and so forth. And this is how people work. This is how we do statistics. And the purpose of this theory is it's really not about philosophy. We can't escape the philosophy in thinking about these things. But the purpose is to really affect the practice of practical statistics. First, though, a word for our sponsor, who is, I think, without question, the cause of why we're here today. So happy birthday, Vijay. This picture dates approximately to the time that slightly later, approximately to the time that Vijay and I were colleagues at Georgia Tech. So it's really nice sharing that time with you. And since. Okay, so now to the sort of tough issues. The issues have to do with the fact that you cannot reason about causality just from correlations. Correlations is what people study in statistics. They try and learn something from looking at correlations, but you cannot from that reason about causation. So this is beating a dead horse perhaps, but I think it's worth going through this. If you look at take a population of teenagers, and you just collect from all like teenagers and you try and do correlations between alcohol consumption and performance on standardized tests, you actually are likely to find that performance goes up with alcohol consumption. So why is that? Why would you think that might happen? Pardon? Age. Thank you very much. Money is on the ball. If you segregate your population by age, you will find perhaps the opposite correlation. But teenagers is a broad group. It goes 13-year-olds through 19-year-olds, and overall, the 19-year-olds will do better on the test. So, okay. So the question, though, is, and this is known as the Simpson paradox. It really just says the Simpson paradox says basically, anytime you have a bunch of correlations and you think you've learned something, you can always like reverse all those correlations by throwing in one more covariate. Okay, there's been famous court cases like at Berkeley based upon this subject, and it's a whole subject unto itself. But this is really just to give a very clear indication that there's no way to tell what's the effect of alcohol consumption on your kids' school performance just from looking at correlations. You need to have somewhat more of a model and get some causality. What's the effect of drinking alcohol? You need to go beyond the correlations and anything else. The toughest technical issue that you come up against in this whole topic, just to give a preview of where we're going here, is this notion of hidden variables. The point is, there are some variables that are affecting the things that you're measuring that you cannot measure. There are some variables you cannot measure, you don't even know what they are. Perhaps, maybe you know what they are, and you can't measure them. Usually you don't even know what they are. And in the sort of most extreme and kind of worst case of all of this, there might be some hidden variable that can affect all the variables that you can measure, right? And if that's the case, then none of the variables that you see are really causing anything in any of the others. They're all just kind of like a shadow of what's happening in the real kind of world up above. And the hidden variables are where all the thing is, we're just watching kind of a shadow world. We can't cause anything in the actual figures by trying to touch the shadows. So that's the extreme version in which there's really nothing you can say at all, but in this theory, we sort of try and get at less extreme situations. So in order to reason about causality, you cannot just look abstractly at a bunch of variables and how they relate to each other. You need an actual model for those variables that selects some of them, including maybe some of them that are hidden variables, and expresses some constraints on which variables can or cannot affect others. And if you have that kind of a model, then maybe, and we'll talk about the maybe, you can go from statistics to studying causal effect. So the mathematical model here is called structured causal models or semi-Markovian models. We'll see how much time we have to get into the technical stuff. But the model basically looks like this. There's a graph. There's a variable associated with every vertex of this graph. It's a DAG, okay? And when an edge is not present, that tells you that tells you something about that there's a conditional independence. So here's what might happen in this model. I don't think any of this doesn't have a pointer somehow. Anyway, so X and Y here are sort of independent, but there's some variable Z that can be affected by both the values of X and Y. Okay, it may have some randomness of its own, but it gets to sort of, so if you want to write the joint probability distribution, P of X and Y and Z is the probability of X. Generally speaking, it would be the probability of Y given X times the probability of Z given X and Y, but in this model, because there's no edge between X and Y, that gets abbreviated to P of Y, okay, because Y doesn't, that's the model constraint. Okay, so X and Y are actually dependent in this are independent in this model. If I go and I change the variable at X, it has no effect on what Y is, but that doesn't mean that X and Y are independent after you observe Z. Okay, observing Z is called post-selection or endogenous selection, and observing it can make you think that independent variables are actually dependent. Okay, so there's for lack of time, maybe not go through, but there are a lot of very clear examples where this can happen. People worry about, are salary offers independent of race? Well, you can't tell by looking at what people earn because that's conditioned on people having accepted offers. And so, I mean, there's a zillion examples of these types of things. Okay, so it makes all kinds of empirical statistics studies very, very challenging, as you can imagine. So that's one case. Here's the next case. I drew the same graph, but you'll notice that the directions of these two edges have now been reversed. Okay, so this is the case where X and Y are both dependent upon Z, but otherwise independent of each other. Okay, so this is what's called that X and Y have a confounding variable. So they're dependent because there's a confounding variable, but they're actually conditionally independent given Z. And again, trying to affect X, making what's called an intervention at X, is not going to affect Y. So for example, earnings and marital status might in general be correlated because of a confounding variable of educational level, but it could be that if you condition on education level, once you condition on education level, it could be that, getting married doesn't affect your earnings, or getting a raise doesn't affect your, these things could be independent of each other once you condition on education level. So these are the sort of things that people struggle through. And finally, the last version of this graph is that the arrow goes from X to Z and then from Z on to Y. And in this case, X really does finally have causal effect on Y through this intermediary. And a nice theorem, which was of Verma and Pearl back in 1988, is that if you slightly generalize these three examples, these are the only three ways that you can get correlation between variables X and Y in one of these directed probabilistic graphical models. Okay, so it's a nice theorem, and it's sort of a technical basis for this theory. I just want to say another historical remark is that this whole business of looking at causal diagrams actually has a pretty long history. It's almost 100 years old at this point. It goes back to the Journal of Agricultural Research, 1921. And one of the things I like about it is that, he's very clearly identifying this issue of causal effect of certain variables of these animals on certain other variables, where the ultimate thing he cares about is like, what's the weight of these guinea pigs at 33 days? So people really do study guinea pigs. It's not just an expression. Okay, so I want to tell you, again, this is supposed to be an invitation to this area. So in the brief time that I have, which is really getting briefer, again, there's going to be very little technical material. I actually maybe care more about actually exposing you to some of the examples where this causality is such a big deal, because I actually kind of think that we have an opportunity to contribute to this area, and it really matters. So, I mean, I really think there's, we really care about things like, should we, what's going to be the effect of putting, more, coal burning stations on the environment, right? Something we can't do experiments in. What's going to be, what's going to be the effect of, pregnant women drinking wine? These things really matter, and they are not, we do, k-means, clustering, and all those kind of things, which are very passive. Here we actually are studying something where there's like an actual much more of a chance for effect if you are looking at causal rather than statistical information. So for this reason, I'm going to treat you to one of the most interesting examples, I think, where causation and correlation kind of conflicted in the public sphere. So there were a lot of studies, careful studies beginning already in about 1928, not only in the United States and UK, those are the places where like a lot of the research was done, but all throughout Northern Europe there were studies. And these studies showed really high positive correlation between smoking and lung cancer, okay? And actually other diseases as well. There's this quote, a very well-known paper by Winder and Graham in 1950, that just pointed out the timing matched. The enormous increase in the sale of cigarettes in this country approximately, this is in the US, approximately parallels the increase of bronchogenic carcinoma, okay? And at the time they had really only just these correlations, but they were, and actually by the way, it was even more finely detailed. For example, smoking picked up first among men and later among women, and there was a suitable time delay in disease. And so the government in the United States issued a series of increasingly strident reports about these correlations, and increasingly strident in the sense that, well, they pointed out first the correlations and gradually started to use the word even causation, okay? But this met with actually a lot of resistance, which is like hard to conceive today maybe. But here is Harry Green, a professor he was the chairman of the Yale pathology department. So this is about as high as you can go in sort of, US academic medicine, right? And he said he was so unsure of any relationship between smoking and cancer that he would continue to smoke until the tobacco companies cease manufacturing their product. The government has only statistics, and the statistical association has to be interpreted. Sort of, you'll pry my cigarette from my cold, dead fingers type of quote. And Ronald Fisher, who is probably a name that we all know, one of the preeminent statisticians of the first half of the century. So he was maybe a little bit of a cranky old man at this point. I'm being filmed, aren't I? He wrote as follows in Nature in 1958. He wrote the suggestion, among others that might be made on the present evidence, that without any direct causation being involved, both characteristics, namely lung cancer and cigarettes, might be largely influenced by a common cause, in this case the individual genotype, was indeed rejected with some contempt by one writer. Although I believe that no one doubts the importance of the genotype in predisposing to cancers of all types. What's lovely about this quote is it's really dead on about the model. He's saying, yeah, people are getting lung cancer. Yeah, people are getting cigarette or smoking. Yes, they're correlated, but there's a common cause. The genotype is making you do both of these things. Okay. This is Ronald Fisher. And here's the diagram that corresponds to what he says. There's some genetic factor called U, which is hidden. So I've shaded the circle in a different color because you don't get to measure that. You don't even really know what to look for, even today. And it affects both smoking and your propensity to smoke and your propensity to get lung cancer, okay? And this played out in court. There were a lot of courts, cases, I should say, about smoking over decades. And as late as 1999, Patricia Henley, got lung cancer, and so the Philip Morris attorneys, the tobacco company, said pretty much what Fisher had said. There's a theory or hypothesis that deals with people's personalities. The same thing that causes people to smoke may just predispose them to lung cancer. And they had this tactic worked out very carefully. Here's a memo from vice president of something called the Tobacco Institute. He says there's something called the constitutional hypothesis that people who smoke tend to differ in genetic makeup or in some other way from people who don't. And then there's another kind of theory that is multifactorial that, let's not talk about that. Constitutional hypothesis is what I really care about. Okay, so this was used in these defenses, and so there's this notion of hidden common causes that was raised as a defense. And by the way, much more recently in 2008, there are actually studies that show slight effects of a common predisposition. I don't know how reliable, I don't know if this is stood up, but it's a logical possibility and may even be true to some small extent. And so what we really need, and what this causal theory of inference, what this mathematical theory of causal inference is sort of supposed to try and provide, is some way in which even when you get a strange thing like in 2008 saying, there actually is a hidden common cause for it, a little bit, you'd like to be able to kind of deal with these things quantitatively. Okay, and that's really the key. So what do I have, about 8 minutes or something? 5 minutes, 5 minutes, a little bit less. So I'll just say a little bit more about what's known and just give a taste of what's known here. So a semi-Markovian model is going to be this thing where it's like a Markovian model, it's a probabilistic graphical model, but there are some nodes that you can sort of draw in the model, but you don't get to observe what the variables are. So that's what we'll call a semi-Markovian model. It would be Markovian if there were no hidden, but these pink things are hidden. And there's an observed distribution where, again, there's some known conditional, where there's some, well, you don't know them, but there's some law. There is a probability law. It says probability of X given its predecessor. So in this case, X has only one predecessor, which is the hidden variable. Okay. So you observe this distribution. You observe just the visible variables, of course, not the hidden ones. And the beautiful thing that exists in this theory, that was a real surprise to me when I started looking at this a few years ago, is this notion of inferring causal effect without doing controlled experiments. Okay, so really the way science has always proceeded, or a model of the scientific method has always been controlled experiments. That's our model. And the amazing thing is that this is a rigorous framework in which you can do statistically defensible inference of causal effect with, sometimes, and the sometimes is what I'm going to say a word about, without controlled experiments. Okay, it's only under limited circumstances. You can't just, but there is this. It does exist as a possibility. So the graph that's drawn over there is one in which we cannot do that. We get to observe this distribution, and what we're trying to infer. What's really the goal? The goal is to go from the observed distribution on, in that case, just two variables that you can see, smoking and lung disease. What you'd like to learn is the intervention distribution. So you'd like to learn it's just a noisy channel, okay? What you'd like to learn is in information theoretic terms, the noisy channel. If smoking, what's the probability of getting lung disease? If not smoking, what's the probability of getting lung disease? That's a noisy channel. You'd like to learn that channel. That's called the identification problem, okay? Now, the question is, on what types of graphs is this noisy channel identifiable? That's the overarching question. And not surprisingly, there are lots of cases where you cannot. So the graph that's drawn here is one in which you cannot do this. But amazingly, as I was saying a second ago, there are cases where it is. So the one I've drawn here is a case where it is, okay? So in this case, I've even written down, I'm not gonna have time to go through it, but I've even written down on this slide this probability of y, this notation probability of y do x, what's written on the left-hand side there, is the parameters of the noisy channel. It's just a conditional thing written on each arc. And here's a formula for it where you see that everything on the right-hand side is using only observed. There's no u on the right-hand side of the equation, right? So it's all just from things that you can actually see in the statistics, okay? So here the case, in this model, what's changed? What's changed is that although x may have a causal effect on y, there's an intermediate variable. Any effect on x on y doesn't go by a direct arc, but only indirectly through z, which we can see, Okay, and so that's really how this model is different from the preceding one. And in this model, it's actually possible. It's not, well, here's the formula. So that's just a small example, but there was a long line of work that ended in 2006 and 2008, where there's a theorem that completely characterizes which semi-Markovian model, probabilistic graphical models, you can do identification on and which not. Or rather, it's not just the model. So you write down the graph and you say which variables are the intervention variables and which disjoint subset of variables are the ones on which you want to know the causal effect. And there's an algorithm that tells you, if I tell you all this observed statistics and I tell you what the subset X is that I'm controlling and the subset Y that I'm want to know the effect on, there's an algorithm that will tell you whether or not the causal effect is identifiable. And if it is, it will actually tell you what the rational map, it turns out to be a rational function from the probability space to the noisy channel. Okay, so that's kind of a great victory in this field due to, if you can read it, Spitzer and Pearl, and independently of Wang and Valtorta. Now I want to say something about, in the last 2 or 3 minutes here, something that I did with Piyush Srivastava on continuing this line of work. So this algorithm I told you about here assumes exact knowledge of the observed distribution and exact model of this graph. That's this model. And both of these assumptions are problematic. Certainly you have only statistical information on the distribution, so you want this to be robust, so that's a question. And second of all, you may not really know that absence of an arc is a very, very strong statement about one of these models. You'd like to know that, well, even if there's a slight effect, I can still save something from my conclusions. So we studied essentially the stability of this ID map. And so here's the question: how sensitive is this ID map to small perturbations of the input? And there's several ways in which you might talk about what that perturbations are. As I said, one is model stability, this business of missing edges. So you can quantify what it means for there to be sort of a weak edge in the graph where very little effect is transmitted. Okay, we're going to quantify this in terms of condition number, but I'm definitely not going to define that now. Another place where errors enter is just floating point errors in a numerical analysis. You might think that that's a small thing to worry about, but it turns out not necessarily. And then there's, of course, these statistical sampling errors. And by the way, there's an interesting additional cause of errors that can come in that, due to some really fascinating work in our field recently, is that you might intentionally have introduced errors into the data because this is through a differential privacy mechanism. Okay, so there's lots of reasons why you're not operating on perfect data, not surprisingly, and not working with the exactly correct model. That's it. So, so here's, I'll just say what the sort of results are. Our main result, it turns out, is a negative result. It says there's a sequence of these graphs with like n vertices in which this causal inference algorithm from a decade ago that I referred to in the previous slide is incredibly unstable. So the condition number goes like e to the n to the 1/2, essentially. 1/2 minus epsilon. Okay, it's the property of the identification map. It's nothing wrong with the algorithms. That's just what this map is. So there are these structured models in which, although in principle causal effect is identifiable, actually it's not so much. So that's sort of unfortunately our main news was negative. On the other hand, so what this means that you'll lose sort of a lot of bits of precision. On the other hand, there is a nice class of examples that are well conditioned. This is a much easier theorem, but maybe actually more useful in the sort of positive sense. So there's a class of well-conditioned examples for which an algorithm was known much earlier for inferring causal effect. There's sort of a restricted class of graphs. And those where the algorithm is easier are also those where the stability is much better. So that's sort of good news. So that's just a taste. Maybe I'll mention some questions. There's actually a lot more questions. I just kind of put down 4 of them. But there's, like I can tell you later, a lot more. First of all, our conditions for stability are probably way too restrictive. There's probably a lot more to do on that. in the case where the channel is unidentifiable, there's still some reason of causal channels. You still might be able to say lots of useful things, like even though I can't get a good enough model of the climate to give you one of these pristine graphs, I might still be able in a responsible way to tell you that building coal-burning factories will cause, unacceptable level. You might, but you want to make these things rigorous, right? People out there really argue with stuff that you cannot defend. They'll even argue if you can defend what you're saying scientifically, but you really should be able to defend them scientifically. So that would make, so item number 2 there is, I think, really important. Question 3 refers to the stability of this thing we just requested in item 2. And then there's a whole class of questions having, all the same questions having to do with what's called structure equation models, where instead of having discrete variables, you say my variables are real valued, and maybe each of the mappings is linear with Gaussian error. They're sort of structured real valued models, and you want to address all of these types of questions there. Okay, I will stop there.
We have time for maybe one quick question.
How difficult is the inference question for given data you want to come up with the most plausible model?
Yeah, that's a great question. There's a whole nother part of his theory. So everything I've talked about has to do with, I know the model on physical grounds. Like, for example, the smoking might cause tar in the lungs might cause a disease, but nothing else kind of causes tar in the lungs, So those are things where you've argued the model on physical grounds, and then you come and do your statistics. People do look at what you just asked about, which is, let me just collect a bunch of data and try on sort of Occam's principle to derive, the most parsimonious graph that would fit the statistics. And there's a lot of work on that. I think, to me, it's philosophically a little harder to get behind that line of research because it's very optimistic, and maybe I'm just being more critical. But I have a colleague who, there's actually a lot of work on that. Maybe just to say one kind of obvious thing, though, all you can hope to identify in those cases is an equivalence class of graphs. For example, X causes Z causes Y, just a Markov chain, a 3-stage Markov chain. From statistics, you can't tell which way the Markov chain is pointing. Okay, so you can never identify the right model. You might identify 2 or several models and say that it looks so much like a Markov chain that I believe from parsimony that that's what I'm looking at.
I vaguely remember the girl giving a talk at UCSD where you talked about finding the max entropy model.
Yeah. It's kind of a big subfield. I think that's only one of their approaches, and I don't have a dog in that game. I don't really have. Yeah.
So the underlying randomness to work with the randomness, because the basic model of the world is determinism, and you spoke about hidden variables according to the Bohmian model of quantum mechanics. Is this correct?
No, I wasn't restricting myself to a quantum type of just. Hidden variables just means you don't get to observe them, you don't get to measure them, you may not even know exactly what they are, but in these models you do say, whatever the hidden variable, it can't affect this. As in this example I just briefly mentioned, tar is just caused by smoking. My genotype is not causing me to have tar in my lungs, that's sort of the thing. It might cause me to smoke, and the smoking might deposit tar, but